Good morning, everyone. I am Francesco Dalena, and I am a group leader researcher at the Laboratoire de Catalyse Spectrochimie de Caen in France. I am truly honored to be here to be a part of this event if I couldn't be there in person due to other commitments that I have in this period. My sincere thanks to the organization committee for this kind invitation. Today I will speak about one of my recent work related to the spectroscopic characterization of black nitrogen and phosphorus doped zeolite template carbon. Zeolite, in general, are crystalline microporous aluminum silicate with highly ordered pore structure, often used in catalyst and separation in some synthesis. Carbon sources are introduced into the zeolite and then removed by calcination at around 550 degrees. In contrast, zeolite templated carbon, or ZTCs, are obtained by using the zeolite itself as a template. After carbonization, the zeolite framework is removed using a mineral acid, typically HF or HCl. This carbonaceous structure is a 3D ordered pore system with a narrow pore size zeolite and exhibits a very high surface area. Thanks to their tailored porosity and surface chemistry, the ZTCs have been investigated for hydrogen and metal storage, oxygen electrocatalysis, or also gas absorption. Their performance strongly depends on the surface functionalities, which is why detailed characterization is critical. Despite decades of work, the ZTC exact structure is still under debate. Several structural models have been proposed, from the high density Schwarzschild-like closed structure modeled by Roussel to the more chemically realistic buckyball-based open-blade model by Nishihara. Other interpretations include Kim's 3D graphene-like framework and this one that is a Fullerene-like cross-linked structure. All these models are supported by various physicochemical techniques like XPS and Raman, which provide insight into bonding environment and carbon hybridization. However, one of the most useful techniques, like FTIR spectroscopy, which could offer valuable information on functional group, especially for oxygen and nitrogen containing species, has been largely underutilized due to the strong absorbance and light scattering caused by the black carbon mass. This black carbon mass effect is a phenomenon that affects infrared and Raman spectroscopy by reducing signal quality and distorting spectral data. The physical origin of this phenomenon is related to the black carbon materials that are rich in condensed aromatic structure, for example, graphene-like domains, that exhibit strong absorbance and low transmittance in the middle and near infrared region. Additionally, the high refractive index and the low optical transparency of the black mass cause a non-uniform light scattering, further degrading the spectroscopic signal. As a practical consequence in FTIR spectroscopy, we have a low signal quality. This means that the FTIR spectra suffer from a very low signal-to-noise ratio. We have a baseline distortion that complicates the correct band assignment. And we have also a spectral overlap. In fact, the weak signal from heteroatom containing functionalities, such as carbon-nitrogen, carbon-phosphorus, and nitrogen-hydrogen, are often masked by the stronger bands from carbon-based group, for example, the carbon-carbonylic, carbon-carbon double bond, or carbon-oxygen single bond. This type of problem was evidenced also in literature. For example, according to Nishihara et al., the early FTIR spectra of ZTCs were limited to a very broad and poorly resolved bands, wrongly attributed to carbon-oxygen. Here we can see a small peak of the carbon-oxygen, carbon-carbonylic band, but a strong one, with a huge post-production done by baseline correction, while in this case we can see only the carbon-carbon bond stretching, but we cannot see any carbon-oxygen related to the carbon-carbonylic group. Zhao et al., in addition, reported FTIR spectra of nitrogen-doped ZTC showing barely visible traces of carbon-nitrogen and nitrogen-hydrogen bands, despite a significant nitrogen content, almost 5%. As an objective in this work, we want to obtain and synthesize three types of ZTC's material. The parent one, a nitrogen-doped and a phosphorus-doped ZTC using Faujas-type zeolite and furfuryl alcohol as a carbon source. We want to optimize the FTIR acquisition for the black carbon materials by adjusting sample conditions. We want to perform a deconvolution for the overlapping FTIR bands to identify functional group precisely. And we want to develop a DFT model based on the buckable dimer structure. And at the end, we want to confirm the nature and incorporation mode of nitrogen and phosphorus species using a combined experimental and theoretical approach. The preparation process relies on faujasite zeolite as a structural template. By modifying the faujasite with nitrogen or phosphorus precursors, prior to carbon deposition, we introduce dopants into the resulting carbon framework. Carbonization under inert atmosphere and subsequent template removal yield, we obtain the final ZTC-based material with several types of heteroatoms included in the carbonaceous structure. To obtain interpretable FTIR spectra, we optimize the experimental strategy for a better resolution of the FTIR spectra. And we can synthesize this experimental strategy basically in three bullet points. The first one is the optimization of KBR and ZTC ratio in pressed pellets to improve the transmission of the sample. We applied also a pellet thickness reduction using high pressure to shorten the optical pathway and reduce light diffusion. And we applied also a strict humidity control with a pre-drying sample at 65 degrees for 320 minutes under vacuum condition to avoid interference from adsorbent waters. We divide, and as we can see, this experimental strategy can give us the opportunity to obtain three very well-resoluted spectra, much more better than that one that was already presented in literature. For a better comprehension of the spectra and all the functional group present in this spectra, we divide the FTIR analysis into three spectral regions. The alpha region, that one that is between 2800 and 3800, we can identify three family of bands. The first one, that one at 3450, is attributed to the OH stretching vibration and is related to the signal that come from the alcoholic group or the phenolic and carboxylic band. This band is especially intense in the undoped ZTC, which is consistent with its higher surface area and higher content of oxygenated functionalities. The other peak that is more present in the undoped ZTC and small present in the nitrogen ZTC, but is almost absent in the phosphorus one, is attributed to the CH stretching of the carbon hybridized sp2, while the region between 2800 to 2960 is related to the strong absorption bands from the CH2 and CH3 groups of the carbon hybridized sp3. The attribution of this linear aliphatic chain is strictly connected with the interconnection between the alpha buckyball that are connected with the linear aliphatic chain of the carbon-carbon single bond. This interpretation is further confirmed by the XPS C1s spectra, which show an increased contribution of the carbon hybridized sp3 with the component at 285, associated with saturated aliphatic carbon-carbon and carbon-hydrogen bonds. The region beta includes overlapping of the carbonylic and olefinic band, but thanks to the convolution and the XPS and NMR data, we confirmed the presence of several functional groups. In this region, the FTIR spectra, we observe two main sets of peaks. One wrongly attributed at the carbon-carbonylic band, here at 1720, and this one at 1592. These, in the ZTC, multiple overlapping bands are found around 1721 and 1707 that are present in all the three samples that are attributed to the carboxylic acid and aryl carboxylic acid, but the presence of the peak at 1739 that is attributed to the Piron group was founded only in the non-doped ZTC and the nitrogen-doped one. The peak at 1592 have the main presence of the carbon-carbon stretching of the buckyball stretching at 1591. But I want to underline that the presence of the peak at 1657, this one, that is attributed to the stretching of the vibration of an isolated carbon-carbon double bond or the non-conjugated one, have an higher intensity in the parent ZTC sample, less abundant in the nitrogen doped, but it is completely absent in the phosphorus doped one. This result is in line with the absorption band corresponding to the CH group in the alpha region at 3043. In our deconvolution model, we include in the nitrogen-doped ZTC three different types of bands. One at 1573, that is related to the pyridine-like structure, and another two bands that are related to the bending of the primary and secondary amine. These bands were difficult to assign directly to the strong overlapping with the carbon-carbon double bond adsorption band, and also for the very low nitrogen-carbon content ratio in the material. The standard FTIR could not clearly resolve this signal, but their inclusion was justified by complementary XPS and NMR data confirming their presence. In fact, we can see that XPS, the N1S XPS, confirmed the presence of pyridine, pyrrole, and amide-type nitrogen, while in the case of P2P, we can see two different types of species attributed to the peaks at phosphorus carbon and phosphorus oxygen bands. The solid state NMR provide further evidence, including peaks for imide, amide, and phosphoric group that support our FTIR assignment. The Raman spectra confirm the retention of the carbon framework upon doping. The slight decrease in the ratio between the intensity of the D band attributed to the Kekulé vibration and the G band attributed to the carbon-carbon stretching of the carbon hybridized sp3 have a slight decrease in the nitrogen and phosphorus doped material. This suggests a mild defect introduction consistent with the nitrogen and phosphorus doping. In order to validate our FTIR deconvolution, we applied a linear correlation method between the experimental peak position and the frequencies calculated via DFT. As shown in the figure, we found excellent correlation coefficient above 0.99 using these DFT models. These strongly support the reliability of our spectral assignments. Specifically for nitrogen ZTC, the model using all nitrogen-containing groups, including primary and secondary amides, as well as pyridine-like structure, shows a much more better fit, an R-square of 0.995, compared to models that excluded the nitrogen with an R-square of 0.891 or considered only amides with an R-square of 0.948. These results confirm that a full assignment of nitrogen species in the FTIR spectra is only possible when combining the convolution with complementary data from NMR and XPS and theoretical modeling. To conclude, we synthesize nitrogen and phosphorus doped ZTCs using faugasite zeolite and furfuryl alcohol as a carbon source. The incorporation of nitrogen and phosphorus was confirmed by XPS and NMR, and clear FTIR spectra were obtained under optimized conditions. FTIR deconvolution revealed amide and pyridine-like nitrogen species, and phosphorus mainly as triphenylphosphine oxide and phosphoric acid. These findings were further supported by DFT calculation. If you are interested in a deeper look at the spectral interpretation and theoretical validation, I invite you to take a look on our recent paper published in microporous and mesoporous materials, scanning the QR code present in this slide. This work is the result of a strong international collaboration between our group and the University of Petroleum of Qingdao in China. We grateful acknowledge the support from the region of Normandie, as well as from the National Key Research and Development Program of China. I would also like to sincerely thank to all my co-authors and my chief, Svetlana Mintova, and the entire CLEAR group for their support and collaboration. And above all, I want to say thank you to all of you for your kind attention.